our discussion from the last session, where we concluded that the Dirac distribution provides a mechanism to include the deterministic quantities under the umbrella of probability or random variables. For that reason, we will not use the uppercase X, which we usually use for random variables. We will use a smaller case X because it's a deterministic variable, and we use this notation to indicate that it's Dirac distributed at value X. So we now move on to the Bernoulli distribution, which is the simplest probability distribution in terms of randomness. It's the most fundamental distribution that captures randomness. You know, Dirac distribution cannot capture randomness. If it is to concentrate all the probability at a single point, how can you have randomness? So how does the probability distribution arise? We have to start with a general setting. Let's say you have any experiment. So first you need a mathematical model for the experiment that will take the form of a probability space, the sample space, the probability measure, which requires an event space. Now the event space depends on your interest. So why do I say this will be the simplest distribution? Is because your interest will be in only a single set A. So all you want to know in any experiment, when you perform an experiment, all you want to know whether the outcome belongs to A or it doesn't belong to A. So that is, A is your kind of success and A complement is your failure. So and of course, because that is your event of interest, the probability measure needs to assign a particular value to that event. So let's use small p for that. So I assume that you have decided which event is of your interest, what will be its probability, and now all I need to do is to define a random variable capturing all this interest in our event space. So the random variable cannot go against the event space. So any random variable definable here must assign only two values. One value to all points in A and one value to all points in A complement, nothing else. So for convenience, let's choose 0 and 1. So let's say we assign 1 to points of A and 0 to points of A complement. So that will be our definition of X. X assign a value of 1. You see the Everson bracket? If the outcome belongs to A, X will assign 1. Otherwise, it will assign 0. You can also represent this in this way. Now, I need to know the probability distribution. The probability distribution can be completely characterized if you know how any Borel set B on the real line will be assigned a probability. So let's say any set you can imagine, be it closed set or open set or half open, whatever, it can be decomposed in such a way that these two sets, one at 0 and one at 1, are somehow reflected there. So B can have intersection with 0, it can have intersection with that 1, and when I say 1 I mean the set, and B will possibly have elements outside these two. So this is all you need. B will be a disjoint union of this set this set, its intersection with 0 set, its intersection with that single set, and its intersection with any other points. Now the pre-image, because we need the pre-image for probability. The pre-image of this set, you can see, will be A complement if 0 belongs to B, because only then you will have an intersection. Why do I say A complement? Because I know X has assigned 0 to all elements of A complement. So easy. Similarly, this other term, the pre-image of that will be A if 1 belongs to B, because 1 has been assigned to all elements of A. Now, why do I ignore this part? Because there, all the elements of B other than 0 and 1 are included in that set, and we know X cannot assign any other value, so the pre-image of that will be empty, and the union of empty with any other set will leave that unchanged. So we can now move on to the probability. Now, just remember, this disjoint union allows us to apply the additive rule of probability. So the probability of this pre-image will be the probability of this part, as you can see, and the probability of this part. Now you will see the advantage, and you must notice here that we have used the Everson-like bracket. Yeah, it is a condition 0 belongs to B, and the middle bracket means that this will not give you a 1 or a 0. This will give you the sure event or the empty event, sorry, the null event, and that kind of filters this event. Yeah, so this Everson-like brackets will filter it if 0 belongs, if 0 does not belong to B, this A complement will disappear from the union. It will only appear when that is true. Now, the probability of this intersection, you know, I discussed it last time, that the Everson-like bracket, because it's either the empty set or the sample space, it has to be independent of any set, and in this case it has to be independent of A complement, so the probability will simply multiply the probability of this A complement and the probability of the Everson-like bracket. We know the probability of the Everson-like bracket is simply the Everson bracket, which means that I'll either get a 1 or a 0 depending on whether that is true or not. And you can also understand why it has this filtering effect, because if this condition is false, this Everson-like bracket will be empty. Empty intersecting A complement will give you an empty, and the probability of empty is 0. How do you see it here? The probability of A complement gets multiplied by a 0. Yeah? So they are telling the same story in different language. Same goes with the other part, you can understand this. And now we know P of A is small p, P of A complement is 1 minus P, and you can recall from the Dirac distribution that any Everson bracket can be seen as a Dirac measure. So the Everson bracket corresponding to the question of whether B includes 0 or not is the same as the Dirac measure concentrated at 0. So the Dirac measure concentrated at 0 as a probability measure, when applied to B, it will either assign all the probability 1 if B includes 0, because it has to be concentrated at 0, otherwise this will return 0. Same goes with this one. The Dirac measure concentrated at 1 will check whether B includes 1. Yeah, the answer will be 1 if B includes 1, otherwise 0. So just think about it for a while. We have now a complete expression for the probability measure, because it applies on B, so just read this without B. So let's see how can we express Px itself as a probability measure. So Px, if I ignore B now, because I know it will be applied to B anyway, so Px is simply the sum of this probability measure. And what is that? the Dirac measure concentrated at 0 or located at 0, weighted by 1 minus p. Why? Because 1 minus p is the probability attached to 0, plus the Dirac measure located at 1, weighted by p, because p is the probability is associated with 1. So now we have a very cool connection between two Dirac measures, each located at a single point, and we just take the weighted sum of them, or you can say a linear combination of them, and you get the probability measure for our new random variable. That is what we mean by the Bernoulli measure. So our Bernoulli measure is simply a weighted sum of two Dirac measures. And what does that tell you? We can have a dedicated symbol for that, rather than writing px, because x can mean anything else. Similarly, I mean, if you remember, we have a dedicated symbol delta for the Dirac distribution. So we can have a dedicated symbol for the Bernoulli measure or Bernoulli probability distribution. So we'll write BER with a subscript P, because P is the parameter. And it's a probability measure, so when it applies to B, it will give you this result. We already derived that above. And this is another way of writing the expression for the measure itself. Now, when we know all of this, we can write everything we need for the distribution. So the support or the countable set, the strictly positive discrete density, we discussed this so many times, and the strictly increasing cumulative distribution function. And that's not all. We can even go and recover our actual discrete density. You know how to do that, and our actual CDF, you also know how to do that. Now, this formulation was based on assuming a particular value of the parameter P, the probability of success. Now, we can choose any probability of success, and we will get a new random variable, and all these random variables share something, that they are all of Bernoulli type. So it's better to speak of a Bernoulli family, the Bernoulli family, and each value of P will give you a member of that family. So we have the Bernoulli family of distributions, where you have a member. So the subscript P gives you a member of that family, and P can have any value between 0 and 1, because it has to be a probability. Now, let me tell you a special case of this distribution. What if P is half or 0.5? Can you guess what distribution will you get? You can guess that there are only two values, 0 and 1, and both have the same probability, half-half. So that gives you a uniform distribution. Yeah, of course, not all uniform distributions will have two values, but you just saw that the Bernoulli distribution reduces to the uniform distribution, a uniform distribution to be more precise. So that's it. This was actually the end of lecture 16. I know lecture 16 was already delivered in the class, but I had to set it up in a different framework, and my next video will be about lecture 17, so stay tuned.